here today to introduce our speaker, Chris Sneden. Chris is a professor at UT Austin. He's also a collaborator of mine, and specifically of Dan's. Chris got his undergraduate degree at Haverford College. I've never met anyone from Haverford, so that's interesting. And his PhD from UT Austin. He spent some time at several different institutions in between his getting his PhD and rejoining the faculty at UT. So we were at Indiana, Lick, University of Wyoming, and University of Washington. Interesting sampling of the population. That's excellent. And then Chris
wonderful thing.
Sure. And then Chris rejoined the faculty at UT about the time I was born. So he's been there ever since. That's excellent. History there. I hesitated to say that, but I decided to go with it. So Chris has been very active over the last few years at UT Austin. He's an important member of the department. I will highlight two of his important contributions. One is that, from my perspective, the most important is that he wrote the Moog spectral synthesis code, and almost all people who study high resolution abundances of stars use the code that he wrote a long time ago and has maintained over the years to do the analysis. Chris also, for 16 years, was an editor at AppJ, both letters in the journal, and made a significant contribution to the field of astronomy in that way. I can tell that he is no longer an editor at AppJ because he has spent some time to update his CV, which is very complete, and let me give you this nice introduction. So thank you for that.
Thank you.
And thank you for being here, Chris. We're looking forward to your talk.
Well, thank you. It's good to be here. Jen said we're all working together now, and we're trying. Of course, their projects are centered on M-dwarf stars, and of course the binaries in which there is an ordinary star component. So you probably all heard that from me, but it's the ordinary star stuff which I can do. The M stars just scare the hell out of me, so I would never do that. Anyway, what I want to talk to you today is about the general chemistry of extremely metal-poor stars. And these turn out to be sort of fascinating in the sense, I mean, the general philosophical thing is we would love to know how we got the solar chemical composition. Essentially, that would be the holy grail of this. You start with hydrogen and helium, and how in the world did we get the rest of the periodic table? And that the story of galactic chemical evolution is that. And one of but the thing I'm going to concentrate now is location on this plot. If you believe this vector plot here of the Big Bang all the way to the present day, is I'm going to talk about stars which were formed relatively early. And the reason why, before I forget to mention it, the reason why I like to look at very metal-poor stars is that because they were so early generation, they don't have the bland milquetoast of multiple generations of stars that contributed to the eventual solar chemical composition. There's some hope that if you look far enough back, you can actually see the results in the atmosphere of a star of chemical compositions that were created by a handful, one supernova, things like that. And that's very exciting, because that takes away the problem of galactic chemical evolution. If you've taken a look at galactic chemical evolution models, they sound like an old family apple pie recipe. A little of this and a little of that, and there's so many things you can change that it's almost impossible. That's why I like to look at the simpler early generation stars. I'm going to divide this into element domains. I will remind everybody here of the standard definitions for stellar spectroscopy. Whoops, let's try that. You all know the bracket notation. That needs no more introduction here. But the one that is not quite the standard is the so-called log epsilon. It does get called different things in different places. The Europeans sometimes use a different notation. By log epsilon, I simply mean, in a sense, an absolute number density on a hydrogen equals 12 scale. Metallicity, every time I say metallicity, just think of it's synonymous with the iron group element abundances. And I could care less what the adjectives you put on the metallicity. To me, I'm interested when the metallicity goes below bracket Fe to H of -2. Okay, and whatever there are are various definitions. And they're useful because you try to figure out that you're talking about the same kind of beast. But at this level, I don't care. I want to make sure that you realize there will be a lot of I in this talk, but what it means is really we, and it's a huge number of people that I've worked with who contributed in different ways to the overall results you'll be seeing here. You'd love to be able to describe completely how the galaxy got the solar abundance distribution, not just the periodic table, but the relative numbers of every one of the elements. This is from an annual reviews article, and a couple of plots will come from that, which concentrated on just the neutron capture elements. And I showed here blue arrows that show you the domains that I'm calling the light elements, the iron group, and the neutron capture. And I also pointed out the so-called neutron capture peaks. And the important thing here, just to take away, is that if you're going to have a proper understanding of galactic nucleosynthesis, it's not sufficient just to be able to produce the elements. You've got to produce them in believable quantities. And that doesn't happen trivially. Let's start with the neutron capture elements. These are numerically rare. If you go back to the previous slide, yeah, you add up all of them and you'll get one iron atom. They're numerically rare, but they actually are the majority of the periodic table. Everything with atomic number greater than 30-ish. And the reason why it's greater than 30-ish is that charged particle reactions, synthesis reactions, just start failing very rapidly at this kind of mass. Simply iron's the most stable, iron nucleus is the most stable one. And almost anything you do to it is an exothermic reaction. So basically, we start with the gallium, element 31, being the first of the neutron capture elements. There's a very nice textbook that Rolfs and Rodney put out now. Gosh, it must be 15, 20 years ago now, but it's a really, really nice introduction to nucleosynthesis. And in particular, I've stolen this picture to repeatedly to show, they're showing just for the neutron capture elements, how they get created. We parameterize the different regimes of neutron capture by calling them R for rapid and S for slow. And generally speaking, the slow neutron capture process is if beta decays want to occur after neutrons are captured, do they have time enough to do it before subsequent neutron captures? And the rapid blast process essentially floods, and this has got to be a dynamic process at or around supernova stage, and it's got to be overwhelming all the beta decays, and then the source shuts off, and there's a rapid decay back to the valley of beta stability. And these make different, by pure nuclear physics considerations, there are different amounts of each isotope that will be made by the rapid and slow process. Here's a blow-up of this process just in the near rare earth element domain. And effectively, isotopes like this, 136, oh yes, xenon, I knew that. 136 can only be made by the rapid process, and because it cannot be reached by the slow addition of neutrons, 130, 28, 29, 30, 31, 32, then there's a hiccup. There's no way that the slow process can get to 134 xenon, much less 136. And so what we put here is essentially for the solar system, and that's important to say. The solar system, the fraction of the total elemental abundance made by the slow and the rapid processes can be quite different element to element. The classic so-called S process element is barium, which about 85% of the solar system abundance had to be made by the slow capture process. Only 15% is attributed to the rapid process, and xenon, which is completely the opposite. All in all, about 50-50, the rapid and slow capture processes, but they make different amounts of different isotopes here, given mass number instead of element name, atomic number. But europium, of course, is the spectroscopist classical R process element. Platinum, osmium, gold are R process elements, whereas lead, barium, strontium, those are the S process elements. So you can actually break down the contributions in an individual star of the two processes. One of the joys in working in this domain is that starting in about the late 80s, they started stumbling across wild star-to-star variations in the total neutron capture content of very metal-poor stars. Here's the solar spectrum near 3850 angstrom in the top panel. And by the way, even if you love doing spectrum syntheses, this is a mess, okay? Whereas if you go to very metal-poor stars, I mean, look, they're metal-poor, which means they have fewer absorption lines and less strong absorption lines. But here are two stars which are the same overall iron content, but there are the neutron capture element transitions. There, they're not. We're talking not about a subtle effect here. We're talking about orders of magnitude difference from star to star, which have the same iron content, which have huge variations in the neutron capture element contribution. This is not subtle, folks. If you concentrate on the ones with high neutron capture to iron ratios, you can detect a lot of elements, but you can't do it all the time from standard spectra. And people like Ian Roederer have concentrated on actually gathering, and it's a painful process because these stars are faint, but high-resolution spectra in the ultraviolet, in order to get elements that, generally speaking, you just do not detect in the visual spectral region. So just your random example, just to show you that yeah, we do get niobium, yeah, cadmium, yeah, iridium, stuff like that. And most of these, I confess that even most astronomers think that things like niobium must be just something I made up. But that's, most people don't do this day to day, okay? There are some small victories. First detections of some elements like tellurium in the spectrum of a star. Lutetium, my friend and yours, element 71, I think it is. This is the first believable abundance in any star that we've ever gotten. And that includes the sun. What we've gotten by a lot of effort on certain stars that are extremely neutron capture rich and metal poor is that some of them have a almost pure distribution of the neutron capture elements which have been made by the slow process. And then others, probably the majority of them, are characterized by almost perfect agreement with the rapid process. Now, I always forget to say this, and it's trivial after you do say it to yourself, but don't forget, if I come across a star whose spectrum I analyze and find that the distribution of neutron capture element abundances can be described by the rapid blast process, the star didn't do it, right? The star has a composition built out of a previous supernova, okay? So the stars themselves can manufacture their own slow capture process stuff and belch them up to the surfaces late in life. But they can't do the rapid process. It's run for your lives when the rapid process goes. We can't do it on Earth. There are rumors by the Los Alamos people that, yes, we can do it on Earth, but I don't think they're open to the public about what they've done. You can imagine what the Los Alamos people might have their hands on in order, if they say they have R process data. Okay? All right. So what you get there is a lot of elements. If you go to the ultraviolet and analyze the visual spectral region of a star that is enriched in rapid blast neutron capture elements, and you put down on top of that distributions of solar system, not total abundances of the neutron capture elements, but just the R process components, you get a near perfect match. Here is in the top panel, you have 23 elements. And you could be forgiven for saying, probably these things, if you did your spectroscopy better, kid, you'd probably get agreement. And here is sort of the O minus C comparison. We can't do any better in stellar spectroscopy now. There is, at least among the rare earth elements, and to several elements in around the rare earth elements, there's essentially perfect agreement. There is apparently one way that nature knows how to make the rapid blast process. So the thing you have to actually take rocks and deconvolve carefully for solar system material into slow and rapid blast capture components is here, living, just ready to be seen in some stars, okay? Yeah.
When you say solar system measure, this is probably a trivial question, how are you measuring? Is that the sun?
It's a combination of the sun and meteorites.
Okay.
And the only way you can do basically isotopic measurements is by meteoritic analyses. There is, when you talk to a meteoritic person, you will find out that their abundances are perfect. And then you start pushing a little bit, and you say, no, wait a minute. When we talk, have you ever actually looked even at Wikipedia and actually talked about the carbonaceous chondrites? Because look, the carbonaceous chondrites are the ones that everybody says are primordial solar system material remnants, right? Not the stones, not the irons, but the carbonaceous chondrites. Do you realize how few of them have ever been analyzed? We're basing it on like 6 or 7 rocks that hit us in the head. And I keep asking the folks, is there no variation? And they keep insisting, no, these are perfect. But I would exercise caution here. But what I can tell you is that this star, very metal poor, the overall metallicity is like -3, 3 orders of magnitude less than the solar. If you take its observed spectroscopic abundances and you lay on top of it the abundance distribution of rapid, or what the meteoritic people will tell you are just those components of meteoric material that were made by the rapid blast process. I mean, look, these are completely independent data sets, and they're fitting like gloves. So nature knows really a way to make the rapid blast process. Credit where credit is due. Not to me, although my name appears here, but I'm the happy recipient of a huge amount of laboratory atomic physics work by basically the Wisconsin group, Jim Lawler and his collaborators. They went back starting in the late 90s and did the work that, frankly, physics people don't respect them for because it's considered old-fashioned work. And they did the hard analyses of the spectra of the neutron capture elements. And they produced incredibly precise transition probabilities. And every time you have concerns in astronomy about the viability of spectroscopic analyses, people worry about 3D hydro effects, people worry about departures from LTE. When we do element after element, every time the Wisconsin group and others, there's a group in Lund, there's a group in London, every time they produce more reliable transition probabilities, all of a sudden everything fits. So these are the real heroes of the recent work here. And without them, we'd still be having great stellar spectra and trash abundances. Well, if I go back here, you say, okay, how do we actually interpret the abundances we see other than, yeah, it's rapid blast processing? But nobody can really tell you where this stuff comes from. They know. They know it has to be something associated with supernova blasts because that's where you get the requisite neutron fluxes, that's where you get the requisite densities, stuff like that. And the R process, notice here, oops, big question mark. And that's because they're not sure. The energetics never seem to add up correctly to produce the R process abundance distributions. So in some way, this is still a modeling effort, so be careful there. But they're supposed to be somehow in what they call a neutrino-driven wind. And I think if you go to a lot of theoretical papers, there are a lot of different definitions of what a neutrino wind is. Okay? But the good news is that it's not just hopeless theoretically. The good news is that theoreticians who have some data on the reaction rates, at least in the least R process of the elements, isotopes, and they apply their modeling of supernova neutrino winds, they're actually getting pretty close. And so this is not, now the two curves here are not scaled solar system data, but they're rather ab initio predictions of what should come out of supernovae. And this was a paper by I can't pronounce it, Siglaria Mello and a bunch of people. And the point here is when they actually have supernova modeling from Wanajo and his group, then they're actually getting toward the point at which they can say, yeah, we sort of know at least the physical conditions that are going on here. There are other modeling efforts that have produced essentially the same results. Here is a paper by Carl Ludwig Kratz and collaborators, in which the dots here, oops, I hit the wrong button. The dots here are the mass numbers of the isotopes of the neutron capture elements. And the neutron capture peaks, where the abundances pile up, are very obvious in this picture. And to those points, they attempt to model R process predictions. And you can, hindsight's being 20/20 here, it can't all be essentially an equilibrium process with one temperature, one density, one pressure. You have to invoke a variety, a superposition of different temperatures and different densities. But the takeaway point here, and here on the left-hand side, they start with just the ones that are the highest density, and then they add components which are lower and lower density. And this one, they just start with the lower density neutron capture components here, which makes the lighter elements, but not the heavier ones. And a happy result is here. Now, it's a happy modeled result. It's not perfectly internally consistent. Matter of fact, it has nothing to do with internal consistency in making a neutron star blow up or a supernova blow up. It is just, look, this works based on what reaction rates and temperatures that we can model. But it actually fits in a surprisingly small range of neutron capture densities and temperatures seems to work. So we know we're on the right track here. Now, we should pause here and get somebody to tell me what I've written there. This is the audience intimidation slide.
You want the Italian?
Yeah. What,
well,
basically,
it's a commentary on the male-female dynamic.
See, she knows. He knows, sorry. and the point is, così fan tutte basically loosely translates to they're all the same. And they were talking about young lovers in this case. But what I'm using this for is actually something serious. If you go to look at stars and analyze them with high neutron capture excesses and R process variety, not S process, you get tired of the exercise because they all appear to be the same. And at some point you say, there's got to be a better way to make a living than doing this. And because that's the question you have. R process rich stars was a hot topic, in the 1990s to 2000s. And the natives are restless now, okay? So if you say, well, is everyone the same? And the answer is, well, there are some things still left to do. We know the general shape of the R process distribution. We know that there are tons of stars out there and still to be found with R process enrichment early in the galaxy's history. So the question you have is it even worth finding any more? Don't we know the answer? Well, not really. There are three things that I want to point out that are sort of current things that you might want to think about. The scatter in the so-called light neutron capture elements, and I'm talking about in the atomic number range 30 and 40, typical strontium, yttrium, zirconium, those are the easily spectroscopically accessible ones, compared to the heavies, which are typically barium, the rarest, barium, europium, all those sort of things. There is some scatter, and the scatter gets worse as you go down in overall metallicity. So this is solar, no scatter at all, because you've sort of averaged over n generations. By the time you get below a metallicity of -3, notice that the scatter is getting enormous. Again, this is a signature of fewer and fewer events in an early galaxy which was not well mixed. Okay, that's number one. You do want to understand what's going on there. And there was a paper by Claudia Travaglio et al. That just for want of a better understanding of what could be happening with the lighter neutron capture elements, created this acronym just for the purpose of making it simple in the paper, LEP, and it's gotten a life of its own. Everybody at the conferences talks about LEP as if it was a real process. LEPP means we don't know what we're talking about, okay? That's what the acronym stands for. But that's the thing. The other thing, next thing, Ian Roederer had this interesting updated letter in which the picture would take you about 10 minutes to sort of interpret. But let me just use the picture to argue that the basic point is, and now it's just a strontium abundance and a barium abundance. And if the ratios were the same as, say, in the solar system, then strontium to barium would be sort of zero-ish. So you start at high metallicities, and now you start dropping the abundances of strontium and barium. And now you're dealing with serious halo stars, because strontium and barium are now down by 2 orders of magnitude. And you keep going down, and now you're 4 orders of magnitude. And the point is that we're not even sure we've run out of stars at low enough metallicities that you could say, okay, this before the galaxy started making neutron capture elements. We do not know right now if there are any stars in our galaxy that are completely devoid of it. How quickly did the first supernovae begin to make the exotic neutron capture elements? We do not know, and it's Ian Roederer's contention that we have yet to find that limit. It may exist, like there are famous Nature paper will show metallicity -7 star, the most metal poor star ever until next year when somebody finds -8. And you won't find the neutron capture elements in those spectra because they're just too weak. But are they absent? Because they don't produce measurable absorption doesn't mean there isn't an atom or two in the atmosphere. So we don't know that answer either. So that is something to pursue in the future. Either hammering away at the ones with just upper limits to see if there's how far down you can push the answer, or just going and trying to get better data on new stars. Okay, well, if you go to stars now, which have R process element distributions, and that means among the neutron capture elements, you can guarantee it's an R process and not a slow neutron capture. Yet, go away from the stars that are hugely enriched in the neutron capture elements. Go to ones that actually might even be kind of deficient, but still showing a sign of being made by the rapid blast process. Then your easy assumption that compared with the solar system R process only abundances, that you get an absolute flat distribution. No, you start seeing a tail off toward high atomic number, high mass of the absolute numbers of the neutron capture elements. And it's not, again, it's not a subtle effect, folks. These are order of magnitude things. So this is one of the classic R process rich stars, and it's an exact match to the solar R process only distribution. But there are other stars, equally famous now. Honda and company did very nice work on these 2 stars, that show that there's a huge fall off over just the rare earth domain. So what is causing this? And of course, Ian loved this spaghetti plot here. But the point is that each one of these is a different stellar distribution. And there's normalized to strontium, and some of them are exact matches to the solar. Some of them are very, very different. So, it has become a term which has taken on a life of its own, I think coined by Dick Boyd, and called the Truncated R Process, in which the neutron density conditions necessary for the R process do occur, but they rapidly fall off, and you don't get the rapid neutron blast process proceeding out to, say, uranium and thorium. So there's a huge truncation going on. So that's the question. If you go to the Boyd paper, Boyd tries to, again, repeat the things that were done by the Kratz experiment, in which they do superpositions of neutron capture R process abundance distributions that are different in density and temperature. And you can add them all up to get different answers. Okay, so take a look at that paper if you want more details on it. And again, I just remind you that some of these are like this, and some of them are like that. And so those exist, and they're all out there. You can just over and over and over again. So if I were actually going to continue this kind of work, I would focus on those three areas. Here's another problem. I'm tired of this stuff. I mean, I did it, but doing an full abundance distribution that is believable for 23 neutron capture elements, it makes you, I mean, suicide is the only thing you're thinking of after you do synthesis, after synthesis, after synthesis. Here are the number of lines that were involved in one, but this is one of the R process rich stars. I mean, come on, 52 neodymium lines. Couldn't we have done with 51? So is there an easier way? Okay, and that's to take advantage of the spaghetti diagram. And I'll just simply leave you with this. Oops, I left off down at the bottom. This is the master's project of Mark Schobel, a UT grad student, in which the idea is, look, why couldn't we just take a few elements to characterize the slope? Because all the distributions seem to look the same, except in that slope. How fast does the R process follow? So he's doing a project in which he's saying, look, I'm not going to do 52 neodymium lines. I'm going to take 4 elements. And the 4 elements are strontium, barium, europium, and ytterbium, which I'm sure we all know is element 70. It's near the end of the rare earths, okay? But the point is that by atomic physics considerations, those 4 elements have very simple structures. They have very, very strong resonance transitions and not much else. And the big point is, as you go down in metallicity, as you go down to the -3, -4 range, and you see fewer and fewer transitions, these 4 elements are the last ones standing. And so you could actually use them down to very, very low metallicities when things like lanthanum, dysprosium, they've disappeared. They're just too weak. So I don't do this stuff anymore. Mark Schobel is going to be working on this as a proof of concept. And I think the money is not to be gained here on more detailed abundance work. I'd be happy to be surprised. I'd be happy to have somebody say, oh, look at this one. But I suspect it's not going to happen. Instead, I've turned my attention away from the neutron capture elements to the more prosaic iron group elements, which I define here as scandium atomic number 21 through zinc atomic number 30. Now the boundaries here are fuzzy. Different nucleosynthetic processes contribute a lot to different elements. Titanium is always an oddball element. It can be made at least 3 different ways. We've never really decided how much it belongs in the iron group and how much it belongs in the so-called light alpha element domain. But that's the group I want to talk about now. Now, I've said in many talks, isn't it weird that I can tell you the abundance of dysprosium in a metal poor star better than I can iron? I mean, this is silly. And the scatter and the believability of iron group elemental abundances is not what it should be when we have such beautiful distributions for the neutron capture elements. Well, this Andy McWilliam basically started off the whole interest in the iron group elements because this is a famous plot from an annual review that Andy did. He showed for the first time that below metallicity of, say, -2.5-ish, there are abrupt and large changes in the relative abundances of iron group elements. They do not reflect the solar ratios. The solar ratios in each case, here as a function of metallicity, are basically these red straight lines. And with respect to those red straight lines, there are, again, very, very large changes at low metallicity. Great enhancements for cobalt, drop off in copper, drop off in manganese, and a more subtle, maybe, drop off in chromium. Now, the interesting thing, of course, about the iron group elements is, this is also a follow-up that the so-called first stars group did. Their big summary paper is K. Rel et al., 2004. They used VLT. They got better spectra than Andy had, but they reproduced his general trend, much less scattered. And that was one of the things they were after. Okay, but the same trend, dropping chromium, increasing cobalt. Unlike the neutron capture elements, theorists can routinely produce predictions for the abundances of the iron group and lighter elements, because they can do a lot of the reactions in the lab. They can actually evolve stars to blow up. In other words, from theory, we have quantitative predictions. And this is by Shiaki Kobayashi and collaborators. But there are other predictions as well. But what she shows here is that she actually has predictions for what the manganese to iron will be. She actually has actual numbers, which no one really has for theory among the neutron capture elements. Okay, so here's from her paper again. And ignore the dotted line, that's sort of interest only to the true believers in worrying about theory. But look at just the solid line here compared to the data. The data are just various abundance results among the iron group elements from various studies. And you'd say, well, that's pretty good. Can't we just quit on calcium? Aren't we done? And for silicon, yep, those are predicted pretty well. Not really. The trouble here for chromium is that unfortunately, chromium has provided more information than we really wanted to have. It provides 2 stages of ionization that can be detected in very metal-poor stars. And they don't agree with each other. So is chromium underabundant, like Andy and K. Wells said, or is it sort of not underabundant? And it depends which features you look at. And that's the frustration. As a matter of fact, there are papers suggesting that all of the transitions of the iron group elements, especially those of the neutral species, iron 1, cobalt 1, etc., are subject to severe departures from thermodynamic equilibrium descriptions of the line formation and level populations. So the question is, do you believe anything in this field anymore? And here's a case where I'd say, in the talk about the neutron capture elements, I would simply say observers are way ahead of the theoreticians. I think here's the opposite case. Theoreticians, I think, of modeling of high mass evolution are way ahead of the observers here. Because there is not one way an observer can guarantee an iron group elemental abundance set at low metallicity. Okay? Here's Maria Bergamon's corrections to the cobalt trends in metal poor stars. She takes points like this and says, no. When you do the NLTE corrections, they're way up there. Do we really think that among metal poor stars, there's a factor of 10 overabundance in cobalt compared to iron? It may be true, but like the so-called Scott's verdict, not proven. Okay? So this is a worry. And if you put the Bergamon trend, the observed points without her corrections, and you put the theory as the law at the black line, I mean, it's fantasy land, folks. We have no way of challenging the theoretical predictions with the state of these observations.
Is there a high suicide rate amongst workers in this field then?
Well,
Like
it's
worse
all
than
a question.
dentistry?
It's all a question of employment. As long as you can get paid. I have very low standards, and I've met them. Right? So, here's one thing, and I won't bore you much with the spectroscopic details here, but this isn't the place for that. The problem is, if you look at a very metal-poor star, and again, the examples that are neutron capture rich stand out like sore thumbs. But to the ordinary run-of-the-mill metallicity -2 to -3 star, and you look at a visual wavelength spectrum, and there just isn't much there. We all know that. And so it's tough to even get any of it. There are many metal-poor stars without a lot of the iron peak elemental abundances because they're all undetectable transitions. Here's where the detectable transitions of the iron group are. They're down in the ultraviolet. And that's why the HST crashed to the ground. It's a beautiful machine for going down and for very metal-poor cool stars the spectra are actually not a mess. You can actually work with these. For a solar metallicity star, has anyone ever looked at a high-resolution solar ultraviolet spectrum? It is incredibly bad. I mean, it's a rich spectrum of everything massing on top of each other. But for metal poor stars, you can actually work with individual transitions. So there are a few, and growing, archive, in the HST archive, spectra of very metal poor stars with tons of neutral and ion transitions of just a huge number of the iron group elements. So that's where you've got to work. Okay? Ha! But if you have bad lab data, who cares? Don't even bother. And that's why the Wisconsin group is, as I say, to the rescue again. And here are their past triumphs: titanium, vanadium, manganese, etc. The current one that is being worked on by the Wisconsin group. When I say the Wisconsin group, typically what they will do is send me lists of their new transition probabilities, typically 500 to 1,000 of them, that are all good to better than 10%. Effectively, error-free compared to the astronomical error sources in the spectrum, okay? So they're working, they promised Cobalt 1, summer 2015, then Cobalt 2. What's the punchline that, I just give you one example, okay? Once they get their transition probabilities, then they send the spectra to me. I redo the solar abundance from the solar photospheric spectra, and I also pick one metal poor star as an example and try the same trick. Here is a star, HD 84937. It doesn't mean much to most people. I will say it has been studied to death because it is the one star that spectroscopists have argued endlessly on about the lithium isotopic ratio. But for that reason, we know down to the nearest 1 Kelvin what its temperature is. It's got good Hipparcos parallax. It's a really well-known star. All these are different neutral and ion transitions of titanium. The important point I want you to see here is that you get essentially perfect agreement between neutrals and ions. You get all the way from 5,500 angstrom down into the vacuum ultraviolet. You get the same answers. So there is no non-LTE effect here. They are giving precisely the same answers. That means you can actually say, yes, I do know what the titanium abundance is. So I will stand on that. Okay? Alrighty then, let's wrap up here with sort of a more hand-waving discussion.
Before you move on, are you sort of implying here that the non-LTE corrections from the previous work were overestimated?
I think they are.
Yeah,
I think they are. I mean, I can't.
And that it's more of a problem of just understanding the
Yeah,
transition problem.
one of the issues here is that to do a non-LTE calculation, the one rate that they have trouble with is hydrogen collisions. And so they have to sort of model that. And I don't think anybody's going to be unhappy when they realize this. I don't think even Maria Bergman would be unhappy if we showed that the correction was small. What it would do is allow her to fine-tune her modeling.
What is LTE?
Local thermodynamic equilibrium. It is the cornerstone of all beginning stellar atmospheres work. To be sure, it is essentially an assumption that collisional transfer of energy is much more important than radiative. What this allows you to do is to use the standard Boltzmann and Saha equations to get the populations of the different electron states in different species. And it allows you to use good old Planck function for the source function of radiative transfer. We know it's got to fail at some level. I mean, if you think about the conditions that occur in stellar atmosphere, you say, wait a minute, that's not high density, but it works. And that's partly because it's so, that's why they're local. Okay? Is that help? Sorry, I should have said that. Alrighty. Lighter elements. Those are the light elements I'm talking about. Simply, they're the spectroscopically accessible light elements. They're often a bear to work with visual spectral data. Of course, you get what you receive on whichever spectroscopic region you study. And I'll have one example with silicon. But some of these elements are frustratingly difficult to get accurate abundances for if you only have visual wavelength data. Okay. Many of them are actually in the infrared. And that's what I wanted to tell you about, which is, I'm sure you may have heard about the advent of IGRIS, the Immersion Grading Infrared Spectrograph. It is a project involving the lead investigator at UT is Dan Jaffe, who one of his contributions to the whole field is immersion, high dispersion shell immersion gratings, which allow very, very small spectrograph to get high spectral resolution. And it's the group at UT is complemented by a group at CASI, Korean Astronomical, I'm sorry, I can't remember the rest of the acronym. But it's a joint team involving Korea and UT. And here is just sort of modeling pictures. It's for the entire H and K band. It's a high resolution 40,000. It's got a pleasantly wide entrance slit, about 1 arc second. No moving parts, because it gets the entire H band and the K band, which I'll show you. Oh, I do show you an example for the K band. This is the entire K band. It goes from 2 microns, 2.0 to 2.4 microns. To either side, there's blocking by the Earth's atmosphere. What I show you in the picture are 2 stars, one of which is a very, very metal poor star, and I've shown the arrow to highlight that. It's a star which is a famous K giant. But the important point about this star is its metallicity is near -3. And here's sort of an ordinary giant star. Here you can see the CO band heads, and you can actually still see them in this very metal poor star. The entire bands. So that's why there are no moving parts. What would you move? Because you've got the entire spectrum. I have never, ever personally witnessed an instrument planned, funded, delivered, on budget, on time, working exactly as advertised. I didn't know, this doesn't happen. But this is a beautiful instrument now working on the 2.7 meter at McDonald. Okay? The rest is not as interesting to us. Okay, here's an example when I say that sometimes infrared has better spectral opportunities for the light elements. Silicon, and don't get me started on silicon. It's a tale of woe, but just trust me, you don't even want to touch the 2 lines that are easy to detect in the violet, because they have analytical problems that are just almost insurmountable. Now, they're good examples of where Maria Bergamon's work must be correct. Elements, species that have strong coupling to the ground state and not much in the excited states are prime candidates for departures from LTE. So this star, very metal poor, has 2 available silicon-1 lines, but I could spend a half an hour telling you why they give unreliable answers. Here are the spectral lines, 4 of the 7 that I found in this same spectrum, 4 in the yellow-red spectral region. Notice the scale here. This is a 5% deep line. 4% deep line. You have to have really good spectra at high signal noise and high spectral resolution even to detect those lines. Here they are. This is IGRIS data, this same star. They're easy to work on. So one of the things you can do is actually do much better work on some of the light element abundance. And the light elements are very abundant. They are ones you'd love to have. Okay, top panel of the left-hand picture here. This is all the iron 1 lines I could easily pick out. These are essentially commissioning run data for IGRIS. So this star, I didn't expect to get scattered that low. So here's sort of the average abundance, and that's almost exactly what people have claimed is the metallicity of HD 122563. So that's a happy result. 3 so-called alpha elements: magnesium, silicon, calcium. The alpha elements are known to be overabundant by a factor of 2 to 3 in very metal-poor stars. It has to do with massive star nucleosynthesis that we can talk about if you have questions later. But they are all overabundant by 0.3-ish, 0.4-ish dex. Here are just the transitions that I've observed with Igrans. They give the exact same answers.
Why can't you easily get the sodium abundance with the sodium D lines?
The sodium D lines have the opposite problem. They're too strong.
Oh.
Therefore, what you're seeing...
Never satisfied, huh?
Never satisfied, right? And especially, sodium is another good example of a resonance doublet connecting to the ground state and very weak transitions above it. So, yeah, those are the ones, that's one of the reasons most of the rare earths are so easy to get reliable abundances for. Sorry, the rest of you can be quiet while I talk with the high-res spectroscopists. Okay, look, if you look at the typical rare earth ionized species, there are bazillion transitions close to the ground state. They, in effect, enforce LTE. Collisions can actually populate all those levels, and they're easier analytically to work with than your traditional elements. Your calcium, ionized calcium, your sodium. So yeah, it's a mess. Right. So it's promising. Again, these are preliminary data. Here is a goodie. We have graybeards over here, and we have the young aspiring folks over there. Is this the way it always is, by the way? I mean, is there a memo that's gone out about it? Okay, all right. Oh, wait a minute, that time's almost up. I'll shut up here. Look, to my great surprise, a very low metallicity, HD122-563, has OH that is detectable. OH is a flimsy little molecule. So I won't say anything more about it, but the question is, why? And it turns out to be a molecular equilibrium and an abundance effect. And, you know, if we have time later, we can talk about it. But OH lines are all over the place. Another one of the dirty secrets of spectroscopy is that when we talk confidently about oxygen abundances in metal-poor stars, they're all from 2 lines, and usually only from 1. And that one has contaminants. The famous 6,300 angstrom forbidden line, that's the entire basis for our work on oxygen in metal-poor stars. And it's very risky. And the nice thing is, with infrared data, you can get tons of OH. And happy news for this particular star, they do give the same answer.
Don't forget OH from the atmosphere as well.
Yes, oh no, the atmosphere has been divided out, thank you. What you're seeing here is after telluric division, after sky subtraction. And by the way, Igrans does that very efficiently by doing star, sky, star, star, sky. All that's done. Oh, you're among the young ones, aren't you? Glad I am. So, here's my summary. There's been great progress. When I started in this many, many years ago, the abundances were just in hopeless shape. Thanks to a lot of innovations, better spectrum, much better lab work, better theory for prediction. We're doing pretty well now. I think I've sort of mentioned this for the truncated elements. I'll stand by my observations, and I really need theory to catch up. It's not easy, because it's hard to do the R process in the lab. For the iron group abundances, I think the theorists could go on vacation for a while the observers catch up. Because I don't think they have any business worrying about how they match observations when the observers can't guarantee them. And for the light elements, yeah, one of the ways out here is to go to a completely new spectral region. So I thank you. I haven't been here since my son finished med school here. That's 15 years ago. It's good to be back. Thank you.